Okay, so we'll start with announcements again. And again, if I'm not projecting loud enough, just let me know. I think I'm reaching all the way back there just fine. All right, so we'll start with some announcements. So the first piece of announcement is the first short quiz is now live. Some of you have already made attempts at it. It opened on Tuesday, so this morning, and it's going to be due on Thursday at 11:59 p.m. The setup is 2 tries, 45 minutes each. For this one, I chose to make it 45 minutes, though future quizzes, they may shorten down to just 30 minutes each. It should be individual work, no collaboration allowed, but you can check online for any resources to research, the questions. The quiz is somewhat coding in nature, and so you're also allowed to experiment with code on iLab. The programming assignment 0 has been out and is due tonight. Currently, most of the class has submitted, so it's 80% of you have submitted. So if you haven't wrapped that up ASAP. Assignment 1 has also been out, and that's currently due in 1 week. So as of today, after today's lecture, the goal is to have given you enough of the mechanical material to be able to tackle both pieces of programming assignment 1, right? So if you've taken a look at the structure of programming assignment 1, there's 2 pieces to it. One is called greedy scheduling. And greedy scheduling, we provided some hint code, some provided code in the sort jobs C code that gives hints to that. And then the second part of programming assignment 1 is called map chain mul, right? Matrix chain multiplication. And there's also a provided code, example code called matrix multiply, map mul, that gives you some template code on how to do matrix multiplication. Right, so after today, after we've covered what you need to know about pointers and arrays, combined with the algorithm background from like CS 112, you should have most of everything to tackle these 2 pieces of the programming assignment 1. And so that's the goal for today. And then on Thursday, what we'll do is, we'll study kind of some of the background for really tackling PA1 in further detail, right? So if you need further hints on how the algorithms work, we'll talk about that on Thursday's class. Okay, so any high-level kind of logistics questions that would be global to the class, I can take a minute now to just address them. Yeah. These slides should be posted on Canvas. It should be live. So double check. It's I see it right here. Yeah, it should be live. Anything else global to the class? All right, let's get to it then. So we're continuing with pointers.c, right? This is our way of talking about pointers. It's a hands-on lab code. And so last time, we got everyone set up on pulling the lab C code from GitHub. So in terms of the mechanics, right? So if you haven't already, you can always git pull from your CS 211 directory. This lab is stored in pointers.c. There is kind of some questions about when you git pull, does it overwrite files that you already have in your directory, right? So the way that git works is if it sees that you have a copy of file like pointers.c, and it sees that on GitHub, there's a newer version of pointers.c, it will do its best to compare the 2 files and modify the file that you have there to be updated to what's available on pointers.c. So if you're at all concerned about accidentally overwriting kind of notes you took in pointers.c, what you could always do is make a local copy, right? You can copy pointers.c, create a copy called mypointer.c, and take your notes there. As for the programming assignment files, right, the programming assignment files, the reason we ask you to take something like the file, the task, colot provided.c, and take a copy of that and turn that just colot.c, is so that if we were to modify colot provided.c on GitHub, it wouldn't overwrite your copy of colot.c. Right, so that's how Git and GitHub would help to overwrite or update your files. Okay, so some background, right? So we talked a little bit last time about pointers is a major piece of the C programming language. It's a way of enabling you to interact directly with how data is stored in the computer. And these concerns about how data is stored in the language and what you're allowed to do to manipulate data, these are essential features of any kind of programming language design, right? And this is the way that C offers. You can compare to things that we studied in Java, like how arrays work and how whether passed by value or passed by reference works in Java. These are going to be very fundamental differences versus the Java language. Okay, so that's kind of motivation on pointers. So we'll get to our setup now again. Right, so in the terminal, I am going to be in our class directory. The pointers lab is in programming assignment 1. And in here, you have the pieces of programming assignment 1, and we have pointers. And as we had before, your source code is going to be in pointers.c. And in order to make the changes and be able to run the program and see the latest changes, you have to always compile pointers.c, right? So you can say gcc.o pointers.c, right? So this is underlying what the compilation command is, or you could always just make, right? So make will run the compilation script and give you the program reflecting your latest changes. So last time where we had gotten to, okay, so last time what we did was we went through generally lessons 1 through 4. I have the really freshest copy. And so what we talked about was, pointers are just yet another number. The picture that we're looking at here is we can diagram what's going on in the memory in these diagrams here, where we show this is our memory space, right? In the contents, we have contents, the numbers that we store, and each of these variables, they have pointers, right? So they have addresses, also called pointers, that refer to where in the memory that they're stored, right? So we started with this example here, right? So we'll go through lesson 1 through 4, just quickly to recap where we were, right? So lesson 1 was basically we have a number of integer type. Integers take 4 bytes, and the number right now we store the value 500 in. You can take a pointer to the number, right? So a pointer to a number here now would be this type unsigned int star, which means this is a number which is a pointer to an unsigned integer. And the way we get the pointer of a variable is we use this operator called ampersand, which basically means address of, right? We don't have a very nice name for it. Typically, we just say ampersand means address of. Okay, so basically you have some content number. And when you say ampersand number, it says, okay, give me the address of number. And that'll give you the pointer value here. right? And so if we run this program, as we did here, +1, grab our number. A pointer fundamentally is this long number. It's 8 bytes long. 8 bytes is 64 bits, and so it's a huge number that it could be. 2 to the 64 is the maximum value. And typically, the C language, you would print it out as a hexadecimal number here. Or you can also cast it to a integer type and just print it out as a human readable number. This is a decimal number here. So that's what the picture now shows, right? So we have a pointer. Don't mind that these numbers don't match up exactly, right? So we have pointer. Pointer refers to where number is stored. And so lesson 2 says, okay, in addition to ampersand, there's also this other operator that we have. This other operator is the star asterisk operator. And for this star, we have a nice name for it, right? So this star operator is called the dereferencing operator. And dereferencing means you have a pointer, and when you dereference a pointer, it says, okay, give me where in the memory that points to, right? So here, this pointer was some long number, and we said, okay, tell me where that points to, and I'll give you the content. Right? So we go look at the picture here. We have our pointer number, and we say, let's dereference this value. Give me where in the memory it points to, and it will tell you it points to this number. The value is 500. It is of integer type. Right? So basically, summarize this up, right? The star and the ampersand, they're opposites of each other. The star gets you from pointers to contents, and the ampersand takes you from contents to pointer, where the address is. Then we talked about a little bit about what pointer arithmetic looks like, right? So because pointers are just numbers, you can add and subtract to them, but they add and subtract in very interesting ways because they're types, right? When we say pointer +1, depending on what the data type that pointer points to, +1 has different effects, right? So here you would think that, okay, pointer +1, that must be +1, right? One more, but actually no, right? If you look at the code, what it did here, when we said pointer and give me pointer +1, it gave us a number that's 4 bigger than the original pointer. And it's 4 bigger because this pointer has a type. It's a type pointer to integer. And because integers are 4 bytes, the next correct and next valid location that can store an integer is 4 bytes higher. We can see this in our picture here, right? So we have this pointer. It points to an integer. It takes up 4 bytes. And if we say pointer +1, instead of going to one more than that, like one more value +1, something that ends in 69 instead of 68, here it says +1 actually goes to something that's 4 more, something that ends in 72 as opposed to 68. Right? So this means that the next valid place to store integer is here, these 4 bytes here. Okay, so any questions up to this point? Right, so this is pointers are basically locations in memory, and pointer arithmetic, depending on how big of a number, what type of number it's storing, pointer arithmetic has different meaning. Yeah. Also say your name, please. DJ. So your question is, if suppose there were a data type that's 3 bytes long, then +1 would go to something 3 bytes higher. Generally, yeah, but there's no data type that's only 3 bytes long. So another example is like, if this number, we declared it as short type, short is 2 bytes, then +1 would take it to something that's 2 higher. Yes, Brendan? So the question here is, if we do this +1, does it somehow modify the original value? No, it doesn't, right? So in the code, when we say pointer +1, here, when we say pointer +1, this just creates a number that is 4 higher. It doesn't get stored anywhere necessarily, right? So if you wanted to store that somewhere, then you would have to be like, we have a new unsigned int type pointer +1 equals pointer +1. Now it's actually stored somewhere. So when you evaluate a value, it just evaluates it. It doesn't necessarily store it. You have to store it into a variable like this before it goes anywhere. Okay, anything else here? What we'll do next is lesson 4, which talks about how the number 500 is represented in memory. Okay, so what we did next was, okay, I told you that number is of, let's see, how should we go about this? So we said that number is stored as a integer type. It's 4 bytes. And these 4 bytes, well, okay, so how is it using these 4 bytes, right? Can we somehow look at each of the values of those 4 bytes? Well, first of all, why is it being stored in 4 bytes? Why is it being stored in 4 bytes? Well, it has to do with capacity, right? So it's being stored in 4 bytes because, well, 4 bytes gives you a nice large number range, right? So with 4 bytes, you can store numbers ranging from 0 all the way to 2 to the 32, which is a very large number. It's about 4 billion, right? And so using 4 bytes, we can store pretty big numbers, up to 4 billion. And the way it's using these 4 bytes is, well, if you look at the number 500, the number 500, if you break it down into its binary representation, so we'll zoom in here. If you look at 500 and break it down into its binary representation, 500 is 256 plus 244, right? And we can keep doing this decomposition where we take the next largest power of 2, and we end up with 500 equals 256 plus 128 plus 64 plus 32 plus 16 plus 4. Okay, so this is, the computer is operating in binary numbers, right? So each digit that it's storing in the computer memory represents whether or not each power of 2 has the value 1 in storing 500. So using this information, right, 500 decomposes to this summation here. We basically take 500 and rewrite it as this number here. So this number, the 0b in the front, emphasizes that this is a binary number. And then this binary number is a bunch of 1s and 0s, right? So on the far right side, this is the 1s digit. And we look at the summation that leads to 500. Is there 1 here? No, there's no 1 here. So the 1s digit is 0. The 2s digit is also 0. The 4s digit, we see here, there's a 4 here, right? So the 4th digit here, this is 1. The 8th digit is 0. And then 16, 32, 64, 128, and 256. Each of these are present in the summation. And so each of them get a 1. So in total, this is 9 digits long, 9 bits long. And another thing that we'll do here is we'll use underscore to chop this number up, right? So this is 9 bits long. It's kind of unwieldy. And so I'm going to put an underscore here after the 8th one to emphasize this is kind of like a comma, right? It's kind of a way to take the number, break it up. You put commas in decimal numbers to break it up. Here we put underscores to break up a long binary number. And this underscore here, I put it after the 8th one because these 8 ones are 1 byte. And this 1 byte gets stored in this location here. Right? So this location here will store 0B 1111 for 1, 0100. And then this additional bit here, this extra bit, that's at 2 to the power of 8, 256. This extra bit is here, 0B 0000001. That's 7 zeros followed by 1 1. So this is the way that it's representing 500 here. Right? And we can convince ourselves of this by using C code and using pointer arithmetic to go inside and inspect how this data is being stored in memory. Yeah, question. Ahmed? That's right. Okay, so the first question was this 0B, right? So what does this mean? So 0B is just like a hint, a notation that says this number is a binary number, right? So another example of this is, notice how here, this, what I'm highlighting here, this is a hexadecimal number. And this hexadecimal number, it starts off with 0x, just to emphasize that this is a hexadecimal number. This is just like a kind of notation convention that we use to emphasize that this is, what you're looking at is not a decimal number, it's instead in some other power of 2. Sorry, in some other base. The second question is about endianness, and I'll come back to that. Okay. Yeah. Sure. Okay. So the question here is about, okay, what is this 0B? Is it real? The 0B only happens when you print it out, right? So this is something to be, that's a little bit confusing, right? Are you saying that the memory in here somehow every time it writes a number, it stores 0B? No, it doesn't, right? In memory, when you have a byte, it's just 8 zeros or 1. And in the computer, everything is always bits and bytes. There's nowhere in a computer where something is naturally taking place using decimals or somehow naturally taking place using hexadecimals. Everything is bits and bytes. It's only when we print it out, like here on the terminal, or here in Excel, where I'm writing this down as an explanation, where I put down 0B as a notation to emphasize what we're looking at here is a binary number or a hexadecimal number. Okay, so what we want to do now is we want to use C code to go in here and convince ourselves that this really is happening, right? Really inside each of these bytes, these are the numbers that are being stored. And the way we do that is through some casting and some pointer arithmetic. So here in lesson 4, what I've done is I've taken the pointer as before, right? Pointer here. Originally, this was a pointer to an unsigned integer type. What I'll do now is using casting, right? So this is the way that we do casting in C. It's exactly the same way as casts are done in Java. We put the type ahead of it, and now the compiler will recognize, okay, this is no longer a pointer to unsigned integer, but instead, this whole thing is a pointer to a character type. And this is now valid to store in this variable here called character pointer, which is a unsigned character type. Right? This casting is important. If you don't have this casting here, it'll complain, this is a dangerous storage. And so you have to make sure that these types are lined up. This is called strong typing. Right? And it's something that we're used to. Java also has all of these finicky rules that it checks for to make sure that you storing values into data is always in the right type. Okay, So why did we move to this character pointer? Well, with a character pointer now, what we can do is in pointer arithmetic for character pointers, this +1 now means something else, right? If we do character pointer +1, character pointer is of type pointer to an unsigned character, and so +1 now actually will increment by 1. So here, lesson 4, right? So in lesson 4, these 4 lines here are printed out in these lines here. And you'll see that this value that we would print out, 0, +1, +2, +3, this time around, it actually increments by 1, 2, and 3, right? It goes from 4, 5, 6, 7. A little bit kind of finicky things here, right? So this is a subtle point, but it's important for you to see that this is happening. These parentheses are important, right? These parentheses are important because if these parentheses are not there, the way that the compiler reads this statement, the way it reads it is the casting only happens like this, right? And that would not be ideal. So the casting here, you have to make sure that it's casting on the whole operation. So a little bit of subtle point. Oh boy. Somehow we have lost the Zoom. Unmute. People on Zoom, hope you can hear me all right. You need the screen share back. Somebody in the chat. Good, I'm back. Great. Let me shrink this out of the way. Okay. Are we back on track? Right, so we use pointer arithmetic to now actually get at the underlying bytes of what's being stored. And now we can dereference these locations, right? So now we can dereference these individual bytes. Let's go to this picture here, right? So now we can actually dereference these individual locations and look at the bytes here, right? So this operation here, this line here is saying, okay, character pointer +1. Here's the character pointer +1. The star is the dereferencing operator. Star is the dereferencing operator. We go from address to content, and now we can look at the contents there. So now we can look at what it prints out for us. Here it prints out each of these bytes. The first byte is 244, second byte is 1, third byte is 0, fourth byte is 0. Right? And so this is exactly what we saw before. Right? So this being stored here is this 1 here. So this equals decimal 1. And this equals decimal 244. And this 1 here being in the 2 to the power of 8th place, well, this is really encoding 256. And so that's how it's storing this number 500, which is 256 here plus 256 here plus 244 here gets you this integer is being stored as 500 in these 4 bytes, like so. Okay, any questions up to this point? So this is up to lesson 4, how bits and bytes encode data, and how you can use pointer arithmetic to inspect each of these bits and bytes. Yeah, over there. Yeah, so the question is good, right? So why does it know that this 1 encodes 256? Well, it depends on the type, right? So if you're treating the whole integer as these 4 bytes like so, then each of these bytes have kind of intrinsically, they mean different things, right? These are the lowest 8 bits. These are the second lowest 8 bits. These ones here, these are the highest 8 bits. And it's only when we change the view, right? We force it to change the view here now. We change the view to treat these as individual bits and individual bytes, that when we come and print this, it doesn't understand that really it means 256. It's printing, well, the value here is 1. This byte is 1. And it's when you treat this whole combination of 4 bytes as a whole integer that it imbues the value that this is actually means 256 onto that byte. That's right, right? So the typing, right? The fact that this is an int type means that these 4 bytes are all linked together. It's one number that has to be looked at together. And so kind of subtly, that's what I mean here in this Excel picture. I put like white boundaries around this to emphasize these are groupings that have to be treated together. Okay, there was one question, I'll get to you next, but so there was one question about endianness, right? So endianness is a subtle thing, which is, well, there's another convention at play here, which is there's a convention of within these 4 bytes, right? So the address counts higher and higher down here, right? So these are higher and higher addresses as I move down this picture. Why must it be so that this here is the lowest byte, and this is the second lowest, and this is the highest? And this is just another convention that's at play here. This convention where this byte is the lowest location, this is called little endian, and that's how iLab. That's the convention that the iLab machine goes by. In fact, most machines go by this convention, right? There are some exceptions. I recall, like if you really dig into it, there are some machines that are still being manufactured with big endian, the opposite convention, but most machines now are little endian. You had the question. Why are we casting to unsigned characters? Okay, so the reason that we're casting to unsigned characters is, right, so why did we go about this casting? Well, we did this casting so that we can modify, we can affect how this addition works. If we did not do this cast, and instead here, instead of working with character pointers, we did 0 plus 1 like so, then this would not allow us to go in there and really inspect, because pointer plus 1, when pointer is a pointer to an integer, when you do plus 1, it'll go from here and zoom all the way down to here, 4 more. And you can't go inside and look at the bytes anymore. It's this casting that allows us to go inside these 4 bytes and look at each one in detail. Yeah. So one more question around here and then we'll move on. I don't get the question here. So repeat. Yeah. Do each of the 4 bytes have a number? Yes. So do each of the 4 bytes have a number that add up to 500? Effectively, yes, right? So the number here, this is storing 256. Right, so 256, it's not equal to 256, it means it encodes 256. And the fact that this is 256 plus this byte encoding 244, 256 plus 244 is what's getting us, this is the number 500. The last two of these are 0, right? Because we are chopping up the number as a summation. That's right. Right. So the disconnect here is what's missing here is, well, this is how we store big numbers, right? So if we had an even bigger number, say 2 million, right, we're going to chop up that number, 2 million, such that there's going to be more numbers in these higher position values. And you can experiment with this code, right? So you can come here, use pointer, and kind of say, okay, let's make this a bigger number, 2 million, and see that, yeah, these 4 bytes easily encode 2 million. It just needs us to put some numbers in these much higher powers of 2. Okay, so let's move on to lesson 5. That's right. So the reason that they're all powers of 2, everything here is going to be a power of 2, right? And I can annotate this, right? So this is going to be the power 2 to the power of 0 is 1. This byte here is going to be 2 to the power of 8, which is 256. This is going to be the 2 to the power of 16, which is 65536. And this one here is going to be 2 to the power of 24, which I don't know what that is. And so this is how, using 4 bytes, you can encode huge numbers. Right? So if you have something that's 2 million, then almost certainly you're going to have to put some numbers all the way out here. Okay, lesson 5, which is pointers are just numbers. Right? So what I'm emphasizing here is these pointers, you can take pointers of pointers, and these pointers are just yet some more variables. Right? So what we're going to do now is we have the pointer as we did before. And I'm going to use the ampersand to take address of that pointer yet again. And so this evaluation here, ampersand pointer, the address of this pointer is going to be a pointer to a pointer. And its type is unsigned int star star. The star star means it's the pointer of a pointer. Right, so you can call this unsigned int star star, or we could say this is of type pointer to a pointer to a unsigned integer. And what does that mean in our picture here, right? So in the picture here, let me clean this up a little bit. In this picture here, what I'm going to do is we have this pointer right here, right? Pointer is currently this value here, what I've highlighted in this box. And now we're going to take the pointer of that yet again. And so ampersand means address of, right? Ampersand means go from contents and look at and tell me what the address that stores that content is. And so what I'm asking here is, okay, give me the pointer and tell me the address that stores that pointer. And so it's going to say, okay, this pointer right now is actually stored in these 8 bytes here in the memory. And give me the address of that. So here is, right, so when we use an ampersand, it means go from content, go left, and look at the address. And here we go. So this is the pointer to a pointer of, and this is going to be of type pointer to a pointer to an unsigned integer. And one subtle thing here is, someone tell me why this is 8, right? So why is this 8 bytes here? Yeah, so the pointer type is 8 bytes. Right? So in this machine on iLab, at the beginning of this lab, we did tell me what the size of a pointer is. The size of a pointer is 8 bytes. It means that in order to store all the addresses that give addresses to the huge memory space that the iLab machines have, we need 8 bytes, 2 to the 64 possible range of values, 64 bits, in order to store these addresses. And this is kind of where, you know, you may have heard things like, okay, 8-bit machines, 16-bit machines, 16-bit era, 8-bit music, things like that, right? So these are different eras of computer architectures, where now this computer architecture is a 64-bit architecture, where it is understood that memory addresses, pointers, are 8 bytes long. Right, so in this picture that I draw here, I put this light box around all 8 of these bytes to emphasize that the pointer is occupying these 8 bytes at a time. Okay, so what we'll do now is we can inspect these values, right? So what I'm going to print now is, go to the code instead, put this on the right side. Right, so what we'll do now is we'll print the pointer to the pointer, we'll dereference that 1 time and print that out, and then we'll dereference it 2 times and print that out. And this is exactly what we see, right? So we have pointer, this is some long number, it's an address, so it's a huge number. We can dereference that 1 time, that gives us another address. And we can dereference it a 2nd time, and this brings us back to the raw value again. And we can look at our picture. Right? So if you look at our picture, right, star just means dereferencing, and star tells us, I gave you an address, tell me what the content is. So we have the pointer to pointer. I dereference that 1 time, so we go from here to the right to the pointer type. So that gives us this line here. Right? Don't mind that the numbers don't match up. Every time you run this program, the numbers change. Right? But the mechanics are the same. And we can go from this pointer and we dereference it again. Right? So this pointer, this is an address, and this address refers to this location here in memory. And we dereference that a 2nd time. It means go to the right, go from address to content, and here we have 500, the number that we originally stored. And we can play some tricks here, right? So all of this, you can do it in different ways, right? So instead of, right, examine this line here. Another way we could have written this line is, instead of taking that pointer off of, instead of taking pointer to pointer off of pointer, what we could have done is, well, this pointer, what is this pointer? Well, this pointer is really originally just a dereference off of the number. So this is going to give you exactly the same behavior. You take the number, take the pointer off of it twice. Ampersand means address of. So take the address of number, and this will give you the same thing. Yeah. So say that again. These numbers, so you're saying whether or not this number here should be the same as this number. Well, we can see what the code behavior does, right? So the question now is, okay, if you really examine this number, you'll notice that this number is the same as this number, right? And can we convince ourselves that when we run the program, this really happens? So let's see in the program if that's so. Right, so this number, where did this number come from? This number was printed out here. Right, so this number ends in 5764. Right, so if you were to hash this number, this would be 5764. And this number here, right, so the dereference value of pointer to pointer, this number here, in the actual execution, you'll see it should come from here. And this number also ends in 5764. Right, so what's being emphasized here is this number is exactly the same as this number. And that's no fluke, right? So this is what underlying, when you write this code, this is what it means. So this number indeed does match this number. Good question. Okay, any questions here? Anything from online? I assume sound is fine. If online sound is not working, let me know. Okay, so that was lesson 5. And what we'll do now is arrays. We're now 46 minutes in. Arrays, lesson 6. Right, so lesson 6, what's the takeaway of lesson 6 here? Forgot that we've got slides this whole time, right? So I just want to make sure that we're covering what we have to emphasize here. All right, so the takeaway of lesson 6 is, well, arrays fundamentally are just sequences in memory. It's just a syntactic construct that allows you to put together several pieces of memory. And we'll study this using the lab. Okay, so what we're going to do now is first, we're going to create an array. And you'll see that we're creating this array using this interesting function called malloc. And what malloc is it's a function that just asks the computer to give you a segment of memory for you to store data. And so what the syntax here is saying that, okay, give me malloc, give me memory allocate a number of bytes. How many bytes? Okay, I want array size times the size of the int number of bytes. Right, so array size here, right now we want to create an array of 3 elements, and the elements are integers. And so for each integer, we need a sequence of 4 bytes. Right, so what this will do is in our picture here, we'll create an array. And we're going to allocate a sequence of bytes like so, where the number of bytes here is 3 times 4, where 4 comes from each integer is 4 bytes. So this is what malloc gives you. Okay. And while I'm here, I'll also emphasize some other things, right? So you can write this as malloc. So malloc is kind of the usual name of the function that we refer to these things. There's a whole family of malloc, right? So it's nice to, for example, use a different kind of malloc called calloc, calloc. And calloc takes, instead, it takes 2 parameters. The first is a number parameter, and the second is a type parameter. So calloc, you could also calloc it like this. Okay, we're going to emphasize we want 3 elements. Each element is integer, and each integer is 4 bytes. Size of int is 4. Right, so this would be an equivalent code, these 2. And what we'll do now is, okay, we'll also do some pointer arithmetic, right? So this code here just emphasizes, just as before, right? Array currently is of type pointer to an integer in star type. And because it's in star type, when we do pointer arithmetic, right, this loop is going to run 3 times. We're going to get +0, +1, +2. And this pointer arithmetic just works the same way as integer pointer arithmetic as we had before, where +1 to a integer pointer, because integer pointers are 4 bytes long, +1 will give you an address that's 4 higher, and +2 will give you address that's 8 higher. And this is emphasizing the fact that this is a sequence of memory, and these additions, when you do pointer arithmetic, it takes you to these numbers. Okay, some more syntax things, right? So we can do a couple things here. This code here, what it's going to do is, well, one way of accessing array elements is using the array notation. Right? So this is the array notation that we're familiar from Java, where we say, okay, given this array, give me the element at index I. And so here, for this array, we're going to set the elements at 0, at 1, at 2 for each of these to a multiple of 211. So we'll store it in memory 0, 211, 422. And we can print that all out. So we can look at the code here just to make sure that that's what we're seeing. Right? So we're on lesson 6, arrays. Pointer arithmetic, when you do +1 + 2, it gives you 4 more. And we can do array indexing just as before. The element at the first element of array element 1 of array is going to be 211 and so forth. And at the same time, you can look at this from the pointer arithmetic view. And so we can also look at this as a pointer where each of these, we do the pointer arithmetic, we go to the memory, and we dereference locations in memory. Right? So this syntax here, star array +0 +1 +2, star, just like before, right? Our note here, star means dereferencing, going from address to content. We'll get exactly the same thing. So 0, 211, 40, 22. Where we go from, if you have the array +2, dereference that location, you'll get an integer, which is this value here. All right, so this is what's the takeaway of this lesson? Well, the takeaway of this lesson is arrays are just sequences of bytes. And once you've created an array, you can access elements of the array in the familiar notation as we had before. Or you could also treat it as pointer arithmetic and dereference locations in memory, and that works exactly the same as working with it as an array. Yeah, question. I couldn't hear the last part there. Also, what's your name? Okay. So how will pointer arithmetic work if you're working with a multi-dimensional array? Okay. A little, yeah, jumping ahead here. So we can try that, right? So let's do pointer arithmetic with a multi-dimensional array. Right? And I think this is the right time to talk about this too. Right? So how will we do multi-dimensional arrays? So let's continue with this code here. And we'll do lesson 6.1, 2D arrays. Right? And we want to create 3x3 arrays, two-dimensional 2D arrays. Each dimension is 3 elements long. And so this array here, we'll call it 2D array. Doesn't like numbers, so array 2D. Well, how do we create a 2D array? Well, what we can do is we now have 2D array, integer star type. And what this calc statement here, what this malloc statement should have is we want to create a 3x3 2D array. And so this type here will now be size integer star, right? So this is a valid statement. So in the picture here, what have we done, right? So in the picture here, what we've done is we've created We've created space, we've requested space for 3 pointers. Right, so here will be 1 pointer. There will be another pointer. And here will be yet another pointer. Right, so we've requested 3 pointers for each row of the array. And these are all of type int star. Right, so int star, the pointer type, and so I've allocated each of these 8 bytes because these are pointer types. So this is another int star, and this is another int star. And what we're going to do now is we also need the columns of the array. Right, so we now have to iterate through each of these pointers and assign to each of these pointers 3 integers. So locations we're actually storing the 3 integers. So what we'll do is we'll iterate through all of these rows. Okay, we'll iterate through all these rows. And now for each of these locations here, what we'll do is we'll actually allocate the integers. Right, so this time around, we'll say array 2D at location I. Right, so this I refers to, as we iterate on I, right, so array 2D sub 0 is this location here on this loop. We're going to say, okay, at this location, allocate memory to store 3 integers, or however many integers you need. Right, so here we'll say calloc. I want to allocate memory for 3 elements, or array size number of elements. And each of those elements is integer types, and integers are 4 bytes long, size of int. Right, so as we go through this loop, what this will have done is it'll have filled in each of these. Array D sub 0 is some pointer. Sub 1 is again some pointer. And this one here, sub 2, is some pointer. And each of these pointers, well, these pointers further point to somewhere else in memory. Right, so somewhere else in memory, we're allocating the columns. So in the memory picture here, at some location for this row, we've allocated 4 integers. So here we're going to have 4 integers. And these are going to be array elements D, ones for sub 0, and this is going to be sub 0. So the 0th row and the 0th column is stored like this. And we can see that further down the array, you have the element for the second element of that row. So row 0, column 1 is here. And then row 0, column 2 is here. And each of these are also typed, right? So I should also emphasize that what's being stored here is integer type, integer type, integer type. And so again, the size of these boxes that I'm putting the border around, it's important, right? So pointers are 8 bytes long, and each integer is 4 bytes long. So the length of these is no fluke. And since this is actually a loop, right? So since this is actually taking place in a loop, this happens a total of 3 times. So we can copy this, and this may seem tedious, but might as well just emphasize it. What's going on here? Let's emphasize what is going on here, which is to flesh out the entire array. Well, what we've done now, this is for the 0th row, and it's going to do this also for the 2nd row and the 3rd row, right? So by 2nd and 3rd, I mean the array index 1 and array index 2. Right, so here we've created the 9 integers for each of for the 9 integers for a 3x3 2D array. And to make this more correct, I should say that these indices should be updated. Okay, so let me pause here just to take questions, right? So do you guys see what's going on here? We're building a 2D array now, and 2D arrays, well, what 2D arrays are is some integers, like the base level array for the data type, and then also pointers to point to each of the rows in the array. I saw a hand hovering here. Yeah. Yeah, so you got it, right? So that's right. So let's put that question to pieces, right? The first part was, let's confirm that the way we're doing this is we're allocating memory for pointers for the rows, right? So the first step here is this is going to be array 2D, and it's of type int star star, right? So the first step here is we're gonna allocate memory for the pointers for each of the rows, right? So we create 3 pointers. Each of these pointers is going to point to the rows, and that's exactly what we're doing. The second kind of follow-up question to that is, but since these rows, they have to contain columns, shouldn't this be much bigger, right? Right here, this is 8 bytes. Why is it just 8 bytes? Shouldn't these be bigger? And the reason it's not bigger is because this just has to store a pointer, right? This just has to store this pointer, right? Array 2D sub 0, the first row, the 0th row, which refers to this location in memory. And only at that location of memory do we then allocate the actual integers for that row. Do we actually allocate the integers in the columns in that row? Yeah. Mm-hmm. That's right, right? So at a general like statement, what you said is right, right? Arrays and pointers, they're just different syntactical ways to get at the same thing. And so we see that happening with here, right? So we can access the arrays or the regions in memory using array syntax, and we can also do so using pointer syntax. There's syntactical ways of getting at the same thing. at a first order, yeah, that's correct thing to say. But you know, the textbook, right, being if you look at modern C, it has. Yeah, so the name of the array is really just a pointer to the first location in the array. So that's the same, that's exactly what it is, right? This name array here, well, array is just a pointer type. It points at the beginning of the array. Yeah, unfortunately, you know, I'm on the Rutgers wireless, and the connection is not that stable. So we'll have to debug that going forward. Good. Anything else up to this point? We're working on 2D arrays over there. Okay. So we haven't freed these things. Yeah. So let's talk about that too, right? Let's see. Let me wrap up using arrays, and then I'll talk about free. Alex, yeah. Yeah. So here we're doing this for 2D arrays of integers. Could this be generalized? Right? Could we have 2D arrays of something else, like 2D arrays of floats? Yeah, of course we can. So floats, you know, we would change the type. And here in this memory here, instead of being an array of integers, this could be other data types, right? So that's possible. And also, could this be other dimensions, right? Could we have even more dimensions here? Could we have 3D arrays? And sure, of course, right? So a 3D array, definitely we can make 3D arrays too, right? So a 3D array, you can just recurse on this code. What would a 3D array look like? Well, a 3D array would look something like this, array 3D, calloc, and here this will be of type pointer to pointer integer, right? And then we then allocate, you know, columns, rows, what's like the next thing up, like whole matrices maybe, right? So we'll create the whole matrices of the 3D array. So what that code would look like here is it's going to be a nested loop. Right? We have nested creation of arrays, and each of them just gets more levels of indirection, right? So instead of creating pointers to locations that are integers, we create pointers of pointers to locations. That's how you would build up a 3D array, right? I'm not going to write out this code in full, but essentially that's the right idea. You can create 3D arrays. This generalizes to higher dimensional arrays, other data types, and so forth. Okay, so what we'll do now is we'll use the array, right? So we've created this array, and well, how do we access elements? Well, we access elements just as before, right? So for int I equals 0, int, I array size, I plus plus, right? We'll access the rows. And then we also want to access columns. So we want to access columns. Let's index the columns by j. J equals 0, j less than array size, and j plus plus. So we'll iterate over rows, iterate over columns, and we can printf each of these, right? So %d because we're printing integers. We'll separate each of the numbers with a single space by adding a space here. And let's actually print the numbers, right? So %d, and how do we access the array? Right? So we access the array by saying array2d, ith row, jth column, like so. And so right now, this printout is just going to write a single row. It's going to be 9 numbers not long. It doesn't look like a array, a 2D array. And so to make it look nicer, we can say also print a new line after printing each row. So this, putting this print new line outside here after each row will break the rows into each of its own new line. Let's compile and run. Desynced because internet connection's not stable. Try again. Okay, looks good. Okay, all right, so now it sees our code. Where did I mess up here? Line 65 complains that this line here, line 65, redefinition, right? So in C, it's not happy when we say int array and int array again. It says, well, wait, hold on, you already gave us, or you already told me to define or declare array size up here. So it doesn't like that. Get rid of that. It points us to line 50 was the previous declaration. Here, line 44, number used but not defined. Line 44. Label number used but not defined. I don't know what this is about, but we'll return this to originally what it was supposed to be, like that. So we compile and run. And let's take a look at what we did with 2D arrays. Right, so 2D arrays, we've accessed all of these, and here's our printout 0, 0, 0. And that's expected because that's what we defined each of them to be. So here we had our 2D array. We can give them some more interesting values. We can say each of these elements is I times 211 plus j, something like that. And run it. And so here we have our 2D array, right? So each of the rows that gets 211 more than before, and each column is 1 more than the previous element in the column. Okay, all right. So there's one more point to be made here, right? So here, this is the array syntax. We can also do pointer arithmetic, right? So this comes back to the initiation questions here, which is, okay, what does pointer arithmetic look like in this case? So how do we get it to do the same printout, but with pointer arithmetic? So you want to give it a try? Well, we can unpack this kind of recursively, right? So one thing you can do is, well, how do we go from this syntax here to, how do we go from this syntax here to pointer arithmetic, right? So this is equivalent to, let's zoom in on this thing here. Well, we could say, we'll focus on the ith element here and dereference that. Right, something like that. I don't know, actually, so I'll have to double check what's the right syntax for working with this with pointer arithmetic. Typically, when we're here working at the 2D array level, it's a lot clearer to be working with it, with this array syntax. But yeah, there is a way to access the elements by kind of this like pointer arithmetic trickery. It's possible, but it gets a little bit messy. Okay, so we've got 4 minutes, right? So let's also talk about one more thing. So there was a question about free. So one of the things working with pointers and memory and malloc is that when you write programs in C, when you malloc, you've asked the program to allocate for you some piece of memory. And at the same time, you have to free those locations of memory. Otherwise, the program will have, it's said that the program is leaking memory, right? You're asking the computer to give you all this memory space. And if at the end of the program, you haven't returned the memory space to the operating system, then you've taken up that memory and it can't be reallocated for other programs. And so when you're writing programs that have malloc or have, for example, here calloc, what you have to do is you also, for every place that you malloc, right? So here we have malloc. We have a call to something like that's like malloc. We use calloc as a different syntax. For every of these locations, you also have to free, right? So it's good practice to basically take where you have malloc memory and just do it in reverse, right? So for every place that you had allocated memory, just free that location. So here we're going to free this piece of memory. And we're also going to free this piece of memory. Yeah, that's how you would do free. All right. So okay, so the question here is, how come we can't simply free array 2D, right? So if you free array 2D, right, so we have array 2D here. If you free array 2D, you will have just freed this piece of memory that you had allocated before. But then remember, in order to construct a 2D array, you had all of this other memory that you similarly allocated. And so you have to free all of this too. So you've got to free these individual elements of the matrix of the 2D array. And then after those have been freed, right, after having freed each of the pointers to these integers, after doing that, you then come and free array 2D. Free array 2D, and then you free the array. Yeah. Sorry, can't hear you. Does this mean things can go out of scope? So yeah, scoping also applies here, right? So these variables that you have, you only have access to them following the scoping rules of the C program. But we can answer that question in live. All right, so we'll end class there. And there's recitation today, so the recitation rules are just as before. And you know, good luck with the assignments and the quiz. Yeah, go ahead. Yeah. Yeah. So section 6, pages. Right. So what we're doing, because everybody can attend any recitation that you wish, and because section 6 and 7 were overlapping, we've made it so that instead of having these overlapping times, if you really want to go to Abhilash's recitation, then it's now Friday. For this time, yeah, you can go to 7, right? So everybody can go to any recitation. You can go to this recitation. For the sorting algorithm, sure, yeah, you can add additional methods. In fact, it's probably necessary in some cases. I'll decide later. Yeah. But right now, you can count on it being due at the time it's due. I'm actually going to work on it. That's to be decided later. It's going to be a class-wide policy. Okay, good luck. Hi. Hi, Tyler. No, it's all decided. So if you check syllabus, I guess yeah, you're referring to this page. Yeah, you can go to pages, recitation office hour information is here. I guess what you're saying is on this page here. Yeah, so yeah, I can update this. Yeah, I just forgot to. Yeah. Mhm. Okay. I think the speakers are on. Yeah. Okay. I'll make sure I project louder. Now let's to get a C++ type vector. So officially, yeah, don't use C++ features. You should stick to the C like core of the language. Sure, it sounds complicated, but if you want to go about creating your own, again, you should be careful. Like you should be sticking to the C subset of the language and not accidentally invoking like C++. It'll compile and run, but officially, yeah, you should be doing it in C. Yeah. Yep.
I was just wondering if you like posted online or anywhere like the exact topics that you were gonna cover. Is that just like
yeah. So topics. So yeah. So the topics on the quiz. Last Thursday's slides officially said that the topics are stuff covered up to this point, right? So up to Thursday, which is, the syntax of a structure of a C program, arguments, how printing works. And those are things that we talked about C, right? And also like the first part of the pointers lab. Yep. Hi.
I'm Alex. I had emailed you about I don't know if you had read my last email.
Yeah. So I think you were asking about topics that you're interested in, right? So I always ask if you're interested in research, like what are things in your CS classes that you found really interesting, like stuff that you would just like forget the time reading about or working on.
So do you think I could come to office hours this Thursday?
Yeah, sure. Or you can kind of stick around. We'll go through everybody's questions, and if you want, we can stick around and we can.
I actually have an appointment.
Okay, yeah, office hours then. Yep.
Yeah.
Mm-hmm.
I'll see you on Thursday.
Yep.
Hi there.
Hi.
My name's Sai. I was just trying to understand the 2D arrays again. So each row is a pointer to a pointer.
Each row is a pointer to an array, right? So each row is a pointer to an array of integers, and so its type is is going to be integer star type. It's a pointer to integer.
An integer array.
That's right.
Okay, and then each row or each column is a pointer to the integer itself.
Each column itself is an array.
Oh, okay, it's another array. Okay.
Which is going to be, well, yeah, it's going each column is going to be integer star type, pointer to integer.
Because, I mean, in my head, I have it like, you have the first row, you have an array, and then each array has contents, and within each array, there's the different columns, right?
That's right.
And so each of those columns are arrays.
Each row is an array.
Okay.
Within rows, you have columns,
Yeah.
right? Each column is one integer.
Okay.
And so when you say each column, well, what's each column? Each column is just a single integer at that point.
When it comes to the second, like the second for loop, we're talking about like the way you were looking at it.
That's right.
The first loop goes through each column, sorry, each row, and then the second one goes through each column.
That's right.
Okay.
Yeah.
Thank you very much.
Yep. Good luck. Hi.
So I got a question. When I just wanted to create a matrix or array, can I not allocate memory for it? Because I don't know how many columns or rows of that matrix. So I just have pointer and keep track.
Yeah. So I think what you're asking is, what if the size of
Yeah, I'm not
the
sure about
arrays
the size.
are
Yeah, I
not determined? Well, if the size is undetermined, well, notice how here, right now in the syntax, we're making it so that the size is going to be from this variable. And so when you say something is uncertain, well, it's a variable. So this can be variable. And so the overall size of the matrix can be variable. Yeah. Yep. Look. Yeah, go ahead. I'm just going to double check the class schedules to make sure that we're not getting kicked out of this room. But go ahead. You got a tar of PA0? Yeah, that should be correct. Yep. Mm-hmm. Yep. Hi.
I just wanted to clarify what the difference between malloc and calloc is.
Yeah, so malloc is the classic one. It's, I'll keep saying the word malloc because that's the typical, or that kind of the classic way of allocating memory. Malloc means memory allocate. Another syntax that I prefer using this class is calloc, which separates the parameters into two, right? So first is the number of elements, and then the second parameter, the second argument to calloc is the size of each element. Right? So malloc, you would just do a multiply, and calloc, you just separate them into two parameters. Yeah. They effectively do the same thing.
Okay. Yeah. Another thing is when you read the 2D array, and I remember you said that like you can't just do it for the array, like the bigger array, just like array 2D, because you have to go out the other memory.
Allocations, yeah,
Allocations.
allocations for integers.
If I remember correctly, in like Java, there was like a garbage collector, which I think had like, it would like kind of clean up any memory which like kind of wasn't utilized. Is there anything of the same sort in C or?
No, there isn't, right? So this is a distinction, this is an important distinction between C and Java. C is fast, right? We say C is fast. What do we mean by C is fast? Well, C, it leaves more things up to the programmer in exchange for you have to do more of these management things. And the program, when it runs, it doesn't do any of this analysis and cleanup for you. So Java has a garbage collector. Garbage collection is very expensive. The garbage collection means that every now and then, the Java runtime has to say, okay, are there any dangling references? Are there any objects that no longer are referenceable or out of scope? And then go and clean up that memory for you. So it will do the freeing on your behalf, but it comes at a performance hit. It'll slow the program down because it's doing it.
And last thing, when I was submitting the iterate, I created the tar file, and then I was like, since I had my iLab in VS Code, I kind of just downloaded it there onto my like PC, and I just submitted it. that wouldn't have affected like the tar file at all.
It shouldn't have, no. I mean, you can always double check, and you can open the tar file and look at it, and just to make sure that it's all exact as you expect. Yep. Correct. Hi, this is you. Hi.
I was wondering if you could go over like the 500 thing and like how that breaks down again. You express that through the zero then.
Sure, so let's do that. All right. So instead of maybe doing 500, I'll do some other number, like 55. So 55 is going to be 32 plus 16. Right, so this is 48. 48, and then plus 7, which is 4 plus 2 plus 1. Right, so I'll double check that work, right? So 1 plus 2, 3, 7, 23, 5, 5. Yeah, so it's this number here. And we write binary numbers. The way that binary numbers work is, well, each of these bits, they have a place value, right? So this is the 1th digit, this is the 2th digit, this is the 4th digit, 8th digit, 16th digit, 32 digit. And so the binary number for this is 1, 1, 1. Is there an 8 here? No. So this is 0, 1, 1. And so we say that 55 in binary notation is 0B, 1, 1, 0, 1, 1, 1. But in the example, we just did this for 500, which is a bigger number. So 500 is special. There's like additional thing we emphasized about 500, which was, it was 0B, 1. And this 1, this is the 256 digit, equals 2 to the 8th. And this is in the 2nd byte, right? So here we have then a whole byte, which has 8 bits here, which would have held even more bits there.
Okay.
Yeah.
Thanks.
Mhm.
Also, I have a question about the submission for.
Yeah.
So I tried to make it tar file twice, but I think one was in like the 2022 directory and one was in like the collab directory. So I submitted the one in the 2022 one.
Yeah, that should be fine. Right. So you should double check, just make sure to follow the directions in the assignment description carefully, and you should be all right.
All right.
Yep.
Thank you.
Yeah. Either. Well, you guys finish the conversation. I'll take this question first.
Problem I had was 0. For some reason, I can't like compile it. I can't compile it. I have like the GCC problem. And
What's the GCC problem?
like I tried to terminal,
Mhm.
and it won't let me compile.
Okay, so then it should give you like an error message.
Like it worked before, and I was compile and test. Test my code, and it passed off everything. But when I tried to do it recently, I don't think it's a problem. That's the thing. Something like that.
I mean, it's probably something with the code, so something you modified in the code. Again, right, so it should give you a detailed, you have to describe what you see.
I can show you. It was X something.
Xcode something, so it could be a configuration type of issue.
Okay.
Right, so I would recommend, right, we're running a little bit short on time here, but I recommend take a screenshot of what you see and post it on Piazza, so we can see what exactly the error message is. And likely this is something your classmates have seen before, and we can help you from there.
Sure. And also, just one more thing.
Mm-hmm.
If I run the command on terminal,
Mm-hmm.
That's what you guys are going to use to grade the assignment.
That's right. So
it's going to show me show if I pass all the test cases or some of the test cases in the terminal if I run it.
that's right.
Okay. And if I pass all the test cases, then I should be good with the time, since that's what you guys are using for.
That's right. Right. So it's all one system, right? Grading, feedback, the autograder. What you see it doing is the same autograder that we use. And so unless something strange has happened, the grade that you see autograder is giving you when you run it is the same as what we will grade when we run it. All of this, of course, relies on the fact that all of this runs on iLab. Yep. Yeah, take a screenshot of what you see so we can see what the error message is.
If there is like a situation where I passed all the test cases and then I get 0 on assignment because like the file is messed up, I like screenshot you like like when I tested it and it showed like all test cases you just
So typically the tar file doesn't get messed up,
okay.
right? That's not typically something that happens, right? So long as you get the tar file just fine, you can submit the tar file.
Okay.
Yeah.
And you guys, if I submit multiple ones, you guys gonna take the latest one I submit. The last one I
That's
submit
right.
before the deadline.
Yeah, that's always how it's all set up.
Okay, thank you.
Yep, good luck.